So, today, for the last few minutes that we have here in class, I wanted to talk about the slope of a function. Okay, and so consider for our discussion here the function y equals 2x plus 1. Okay. Now, y equals 2x plus 1, the graph of this, right? Let's do a little sketch of the graph here. Why not? Okay, let's see. I count 1, 2, 3, 1, 2, 3. Okay. So let's see here. 2x plus 1. So this graph. The graph will be a what? A line, right? Okay. Y-intercept is 1. Okay. And what is the slope of this function? What is the slope of this function? 2, right? 2. Or if you like, you could also say, 2 over 1, your choice there, 2 or 2 over 1. That's right. So, okay, we can use the slope here, go up 1, 2, right 1, get a point, go down 1, 2, left 1, get a point, and then just kind of connect the dots there and create our line. Okay. And that word slope, the idea of slope, right? Right now, I think because we only ever really see slope in the context of a line, we pretty much only associate slope with a line, right? The slope is the rate of change of the line, okay? But actually, it turns out that slopes, you can find slopes of other functions, right? And but it's a little bit trickier, right? Because for any other function, the slope is a little bit harder to grasp, and so that's why we don't really teach about that until calculus, right? For a line, the slope's easier to grasp because the slope anywhere on the line is 2. And so we can ask the question, what is the slope of the line? Well, it's always 2. Wherever you are on this line, the slope is 2. You're going to go up 2, right 1, up 2, right 1, or down 2, left 1, down 2, left 1, whatever kind of thing. Okay, that's the rate of change. But what if we don't have a line, right? What if we have something like y equals negative x squared plus 4? Okay. And we want to know, what's the rate of change of this? What's its slope? What is the slope of y equals negative x squared plus 4? Well, let's get a graph here. See what this thing looks like. So 1, 2, 2. Okay, and so this is a transformation of the graph of x squared, right? What's that plus 4 going to do? Shift it up 4, right? Shift the vertex up 4. So 1, 2, 3, 4. There's our new vertex. And the negative x squared, of course, is going to make it then like the bell shape as opposed to like the U. Okay? And I think we'll have zeros at negative 2 here and at positive 2. So I can put those in as well. And like there as well. So, okay. Something like this is our graph. So what is the slope of this thing, right? Like, how can we even, think about finding the slope here? Well, I think you guys already have a pretty intuitive sense here about what the slope for this might be. So, for example here, at this point, right? So let's talk about at this point right here. At this point, we won't worry about so much about the value of the slope, but is the slope going to be positive, negative, 0 here? What do you think about the slope at this point? What would you want to say? Intuitively, the slope would be what? Negative. Why? It's going down. It's decreasing, right? So we know here for a line, if we have a positive slope, the line is increasing, right? And likewise, if the slope is negative on a line, then we know the slope, if the slope is negative, then the line will be decreasing. So it makes sense in some way, right, that, well, since our function is decreasing here, we would think that at this point, we're going to probably have a negative slope. Okay? Now, the actual value might be harder to kind of think about, but at least we can say it's going to be negative. All right? And you're right. What about at this point, though? What do you think here? A positive slope. Why? Function's increasing here. We're increasing as we go from left to right. Okay? And then there is one place here where you can come up with the exact value of the slope. What is the exact value of the slope here at the vertex? 0. It's right. Okay, we have a 0 slope. Okay, the slope is 0. So you can see here that we were actually asking a bad question, right? The question is not what is the slope, okay? It's not what is the slope, because if we ask what is the slope, that kind of implies that there's only going to be one number, like our line, okay? And unfortunately, that's kind of like the way we've kind of trained you to think, right? Because every time we talk about slope, it's always been in the context of, you know, a line. I guess, granted, you did like in Algebra 2 talk about like average rate of change, so like that's like an average slope and stuff like that. You can use the average rate of change to find the slopes in the sense of a function. But that's average rate of change, okay? Here we're talking about slopes at single points, right? We're not using 2 points there, okay? So anyway, the slope then, right, it can change, and that's kind of the tricky part here with determining the slopes of these things. The slopes are changing depending the slopes are changing depending on where you are, depending on your location on the graph. Okay, so the slope is no longer this static thing, this constant thing, okay? It is now dynamic. It changes depending on your location. And so we have to come up with a kind of a different way of thinking about things here, okay? Now, in order to find the slope of a line, okay, how many points do we need to find a slope using what we know about how to find slope? How many points do we need? 2, right? Slope formula requires 2 points. y2 minus y1 over x2 minus x1, right? But when we're talking about functions, our slopes are changing at individual points. And so that we're really talking about trying to find a slope at a single point here, which is weird because the only slope formula we know requires us to use 2 points. Okay? Well, we'll get into that, right? So how do we find the slope of a function at a single point? Okay, right? That's the big question, right? How do we find the slope of a function at a single point? The answer in calculus is the derivative. Okay? And the derivative is a limit. Okay, so that's how it kind of connects into what we're talking about right now in this unit. It's a limit used to find the slope of a curve. Or of a function, you could say. A limit used to find the slope of a curve. Now, I'm going to show you what that limit is. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay? It's the difference quotient with a limit thrown in front of it. Now, you might wonder, Mr. Wade, where does this come from? What is this like mathematics you've conjured up here? Well, there is a reason for it, and I will explain it. Not today. It's going to come later. Okay. For right now, just we're going to take it on, my word that this thing can be used to find the slope of a curve. Okay, it can be used to find the slope of a curve. Okay. And in fact, the way we're going to denote this, so this limit, because it finds a derivative, and specifically we're in this case, since f is the function that we're talking about here, this is the definition of the derivative of f, right? This is how you would find the derivative of the function f, the slope of the function f at any point. And so another way you could describe that, we could say this is equal to f apostrophe of x, okay? Or how we really read it, f prime of x, okay? So the result of this limit, okay, is the derivative, and you denote it as f prime of x. So that helps us to know that it relates to the original function, okay? This thing that we're going to find called the derivative relates back to the original function f. F prime then means the derivative of f, okay? And you'll see what I'm talking about in just a second here. So we're going to do 2 of these. All right, and we'll just do the derivatives of these two functions that we just talked about right here. So we're going to find the derivative of our first one here, f of x equal to 2x plus 1. Okay, now, it is not necessary for us to do calculus here, right? It is not necessary for us to use calculus to do this because, again, the derivative finds the slope of the function. What is the slope of this function going to be? 2. So we had better, at the end up with an answer of 2, no matter what. It should be 2, okay? So let's just see what happens here, though. So I'll go ahead and set up the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, and now we'll actually evaluate it here. So my function is 2 times x plus 1, but if I want f of x plus h, then it's going to be 2 times the quantity x plus h plus 1 minus, and then f of x, so minus the quantity 2x plus 1, all over h. Okay. So again, just took that 2x plus 1, replaced the x with an x plus h, okay, and then subtract the original function 2x plus 1 all over h like that. And now we simplify this, right? So distribute the 2x plus 2h plus 1 minus 2x minus 1 all over h. Okay, keep in mind it's minus the quantity there, so that minus sign distributes to the entire function. Right. What cancels here? What simplifies? The 2x, the 1s. And so we're left with 2h over h, and then what further can simplify? The h's can, right? Yeah, so we can then say limit as h approaches 0 of 2h over h, and we finally get limit as h approaches 0 of just 2. And what is the limit as h approaches 0 of 2? What does this equal? 2. Yeah. There's no h to plug the 0 in, right? There's no h for us to plug that 0 into, so 2 is our final answer there. Oh, that's great. We already knew that, though, right? No surprises there. Okay. So in this case, f prime of x, the derivative is 2. The derivative is 2. Okay. No matter where we are, the derivative will be 2. Questions on that so far? We'll do the next one now. Okay. This is calculus. All right. So let's do that negative x squared plus 4. So again, let's find the derivative. Of f of x equals negative x squared plus 4. Okay, so same thing. We'll use that limit definition of the derivative, which is our old friend, the difference quotient, with the limit as h approaches 0 thrown in front. Okay, so the limit is h approaches 0 of f of x plus h minus f of x all over h. And now again, we'll plug in our pieces here. So limit as h approaches 0, f of x plus h. So here my function is negative x squared plus 4. So instead of the x, we'll put an x plus h. So negative quantity x plus h squared plus 4 minus, and then we'll subtract f of x. So minus negative x squared plus 4 all over h. Okay? And now we need to expand out that x plus h, right? It's really x plus h times x plus h. And so it'll be negative x squared plus 2xh plus h squared plus 4 minus, it's going to be minus a negative x squared, so it becomes plus x squared, and then minus 4. I'll go ahead and distribute the minus sign there too. All over h. Okay, and then I'll go ahead and distribute the minus sign in front of the quadratic there. So negative x squared minus 2xh minus h squared plus 4 plus x squared minus 4 all over h. Okay. And again, this is part of what makes calculus difficult, is these, a lot of these, there's just a lot of steps here, a lot of things going on that alone they are not that challenging, but together they can, you can miss stuff. Okay, what can cancel here? The x squareds and the 4s. Okay, so we're left with limit as h approaches 0 of negative 2xh minus h squared over h. Okay? At this point, if we did a direct substitution of 0, and for h, we get 0 over 0 still. That's not good. But we can still simplify. What can we do here to help simplify further? Factor in h in the numerator, or you could like break up the numerator over the denominator and divide by h that way. But yes, we're going to factor out an h here. So we have h times negative 2x minus h all over h. The h's cancel. Limit as h approaches 0 of negative 2x minus h. Can we plug in 0 for h now? Yeah. Negative 2x is our final answer. So that's the derivative of negative x squared plus 4. That is f prime of x. So what does it mean? Well, so you get kind of a feel, at least, for the fact that, okay, now the slope of our function is changing depending on where you are, depending on the x coordinate of your location. So if I pull back out that graph that we had, right, let's see if it checks out here. Okay, let's see if it checks out. Okay, so there's our derivative that we just arrived at. This thing describes the slope of this thing. So this should describe the slope of this. Well, let's just check it out. We said at this point we had a negative slope. What's the x coordinate at this point? 2, so plug it in. 2 times negative 2, negative 4. Is that a negative slope? Yes, it is. Right? What about this point? We said we have a positive slope here. What's the x coordinate here? Negative 2. Plug it in. Negative 2 times negative 2? Positive 4. Ah, positive slope. Let's check this one. We said here we had a 0 slope, for sure. What's the x coordinate of this point? 0. 0 times negative 2? 0. We have a maximum there. Okay? And so there it is. It works, right? And so at any point you want to figure out what the slope is, at any point on that graph, boom, you can see what the instantaneous rate of change is. Okay? Using that surface. Okay, using the derivative there. All right? Questions on any of that? Yes. To finish that, yes. There is a homework assignment for this. There's 3 of them that I'm going to have you do. I'm going to assign those tomorrow night, though, okay? If you want. I'll put them up, I guess, tonight if you want to do them or not. But anywho, there is some practice with this.